Okay, so quickly, here's your second video to the conservation of momentum. So we removed the two cover-ups here, and you can see that skater A, right here, when the skaters stand facing each other, both skaters have zero momentum because VI1 and VI2 are both equal to 0. So whatever their mass is times 0 is going to be 0 for both skaters. Therefore, P1 and P2 initially are going to be 0 kilograms times meters per second. There you go on that one. So for B, when the skaters push away from each other, their momentum is equal but opposite. But that means what, guys? That means that they had to push off with the same amount of force towards each other to make each other move backwards. Also, their mass needed to be conserved as well, i.e. constant in the situation. So their total momentum is going to be 0, right? Because you would have like a positive 50 kilograms times meters per second versus a negative 50 kilograms times meters per second. So therefore, the change in momentum is 0. Therefore, momentum is conserved throughout the system. So let's try a sample problem here. Sample problem says a 76 kilogram boater, initially at rest in a stationary 45 kilogram boat, steps out of the boat and onto the dock. Uh-oh, think about what's about to happen. Doesn't say anything about him tying the boat up to the dock. Okay, if the boater moves out of the boat with a velocity of 2.5 meters per second to the right, calculate the final velocity of this boat. So M1 is 76 kilograms. V1, VI1, 0 meters per second. M2 is 45 kilograms. And V2I is 0 meters per second. The boat's at rest as well. If the boater moves out of the boat with a velocity of, so V1F, 2.5 meters per second to the right, so it's a positive 2.5. Calculate V2F in meters per second. So let me get rid of this picture here so we can maximize our working space. So our original equation is delta P1 equals delta P2. So this would be M1 V1I plus M2 V2I equals M1 V1F. Whoops. Plus M2 V2F. Okay, let's reduce this equation, guys. Let's keep this crazy simple. So to keep this simple, it says that the boater and the boat were initially at rest. So this is going to be gone, and this is going to be gone because V1I is 0 and V2I is 0. So really what we just have here is 0 equals M1 V1F plus M2 V2F. Ultimately here we want to solve for VF2. So we want to move the negative M1 V1F to the other side, which leaves us with M2 V2F, which really means negative quantity M1 V1F over M2 equals V2F. So with that in mind, that means that we can plug it and solve through. So this should be negative quantity 76 times 2.5, all of that, over 45. Plug that into your calculators, please. 76 times 2.5 divided by 45. That should give you a negative 4.222. I'm going to write the final answer just right here, although you do understand it should be the next line. Looking at your givens, the least number of sig figs is 2 sig figs. So that 2 is not going to round the other one up. Therefore, negative 4.2 meters per second equals VF2. That should make sense, right? Because the boater and the boat are moving in opposite directions. So that sums this up. So now you should work on your conservation of momentum worksheet, please. The conservation of momentum worksheet.